These are some sample example problems on heat transfer. Here's the first question on conduction, the transfer of heat through conduction. A single glass window pane, 2.77 meter high and that 2.4 meter wide, has this is supposed to be 9 millimeter thick. The temperature at the room is 19 degrees Celsius and the outside temperature is 4 degrees. So it's asking calculate the rate of loss of heat by conduction, and second part is how much heat is lost due to conduction each hour through the window. So this is the side view. So you have a glass window, 9 millimeter thick glass window, right? This is inside the room, which is at 19 degrees Celsius, which is the room temperature. Outside temperature is 4 degrees Celsius, and it's asking what's the rate of loss of heat through conduction, right? And if you want to draw the cross-sectional view, so this is the window, right? This is the window, and this is the cross-section. So it's asking how much heat will be lost per second and each hour. Okay. So, and this is the cross-sectional area you need actually, which is length times width. Okay, so, and law of conduction says we have only one formula for law of conduction. Conduction law, is given by, Q over T through conduction, is depends on K of G. This is the thermal conductivity of the glass, which you can find it from the reference table, and area of cross section, and delta T is the change in temperature between inside and outside divided by the L. L means the thickness here. L represents the thickness of the given material, in conduction, right? So that's it, and you can have all the numbers ready, and so kg is 0.75. You can check from the reference table or from the lecture slide. That's the thermal conductivity for glass. Area is, so it says the glass is 2.7 high times 2.4 meter wide, so that gives you the area. And delta T is the change in temperature. So this is given in Celsius. You can just keep in Celsius actually. You don't need to convert into Kelvin. So even if you convert into Kelvin, you're going to get the difference will be same, 15 degree, right? And even if you convert into Kelvin, because Kelvin scale and Celsius scale have same number of divisions between upper and lower limits. So because in both sides you're adding 273 anyway, so the difference will be 15 degree Kelvin in both. So just make sure that when you calculate the change in temperature, you can just keep it in Celsius or Kelvin. Okay, so the difference will be 15 degree Celsius or Kelvin divided by length means thickness. Thickness is 9 millimeter, but the millimeter means thousand of a meter. So that's the rate of loss of heat through the glass due to conduction. And if you do that, it's going to be a big number, 18.225 watts. So that's going to be 18.2 kilowatts. It's a huge loss of heat. It's a huge loss of heat through conduction. So if you take the infrared picture, and you will see actually the most of the heat will be lost through the window, and and the result is you get during the winter time you get the frosted window actually, right? Because there's a huge loss of heat. And this problem is solved by replacing this single glass window with a double glass window. So the second part of this problem is, so this is the first part, right? Second part of the problem is how much heat will be lost due to conduction in each hour. So you already know Q over T. Q over T due to 18.225 watts. But you're solving, second part is asking how much heat will be lost, which is Q, in 1 hour. So which will be 18.225 times T, and T is 1 hour, right? but make sure you convert into seconds, because second is the standard unit. Seconds, 1 hour has 3600 seconds, right? And that's the total loss of heat in through the window in 1 hour, and that's gonna be a big number. It's a huge loss of heat. 6.56 10 to the power 7, and that's gonna be joules. Huge loss of heat. Now next problem is, now replace this single glass window by double glass window. This is the actual picture of a double glass window. Most of the houses in the cold place has double glass window. You must have a double glass window to save a huge amount of energy. Now it's asking, if you replace the single glass window with a double glass window, what would be the new rate of loss of heat, like this, rate of loss of heat, and this is the design. So each glass window is again 4 millimeter thickness, and separated by 10 millimeter, and this is air, of course. You can solve this in many different ways, but the simplest way to solve is, first we want to find what's the equivalent glass thickness of this 10 millimeter air for the same temperature difference. So we want to find the equivalent glass thickness of 10 millimeter thickness of air for the same loss of heat and for same temperature difference between two ends, right? So we're going to do this. Q by T over glass is equal to Q over T air. So Q over T over glass is our K G A delta T over L of G, and this is K of air. Area of cross section will be same, delta T will be same, because we want to find the equivalent air thickness, converted to glass, that will conduct the same amount of heat per second. So we want to find that equivalent thickness of glass for 10 millimeter of air, and then you can replace everything by glass and then find the new rate of loss of heat. So this will be actually 9, so I should say 9 millimeter, because in the first part actually it was let's see, 4 millimeter thick. Yeah, 4 millimeter actually. It's okay. So then A delta T will cancel out. So we want to find the equivalent glass thickness for 10 millimeter air, right? So that's going to be then kg over k air, right? Ratio times L of air. So let's find out that. So K of G is thermal conductivity of glass is 0.75 divided by K of air. K of air is 0.026. This is just from the physical table, and so we want to convert 10 millimeter. So 10 millimeter, just keep it in millimeter. So if you do that, so this is going to be 288 millimeter. So you can clearly see 10 millimeter of air is equivalent to 288 millimeter, right? To conduct, in order to conduct the same amount of heat, you need a really thick glass actually if you want to insulate the same temperature difference. So then back to this. So this is a series combination of these three, right? Now we can just replace 10 millimeter by 288. So the total thickness is 8 millimeter, right? And 10 millimeter of air can be now replaced by 288 millimeter, and plus again no, this is 4 millimeter, I'm sorry, 4 millimeter, and again 4 millimeter. So total of right, 96 millimeter, right? And then the Q over T through the total thickness, right, is now K of G area delta T divided by the L total, right, for the double glass window, and this is going to be 0.75. Area is 2.7 by 2.4. Temperature difference is same, 15 degree, right? Divided by total thickness is 296 and it's millimeters, so this. So Q over T, the glass is, now if you do this calculation, so it's gonna be really small, actually 246 watts, right? And what is the percentage change in rate of loss of heat? So you have a huge loss before, 18225, right? 246 watts divided by 18225, right, and to 100%. So this is more than actually 90%. The rate of loss of heat will be you know, reduced by over 90%, and it's a big you know, advantage, you know, using a double glass window over single glass window. So here's the next problem. So you have a cooler, picnic cooler, you know, made from styrofoam basically, and it says the total effective crossing area all around, you know, is 0.8 meters square. And the wall thickness is, you know, which is L, 2 centimeter, and the cooler is filled with ice, filled with cans, you know, keeping the inner surface at 0 degrees Celsius. The temperature of the outside temperature is 30 degrees Celsius. The thermal conductivity of styrofoam is very small, almost air, mostly air, right? And this is a equivalent, actually. This is an equivalent picture you can draw. So first of all, what is the rate of loss of heat, or rate of heat flow into the cooler, you know, due to conduction, right? And so it's asking what is the rate of conduction of heat into the cooler from outside due to conduction, and this is just using the formula. Q by T is K, this is styrofoam, right? Area, you are given the effective area, delta T divided by the thickness, right? And K of styrofoam is 0.033, area, effective area 0.8 is given to you, and delta T is 30 minus 0, right, which is 30, divided by the total thickness is 2 centimeter. 2 centimeter means 0.02 meter, and that's the total heat you know, conducted into the cooler from outside. If you do this calculation, is 40 watts, okay, which is watts or joule per second, same thing. Okay, 40 watts of joules per second is conducting. So now the next is, what mass of ice melts in 12 hours? Can it withstand the ice inside the, you know, cooler for 12 hours, the next 12 hours? That's the goal. How much the ice will be melt? And the ice is already at 0 degrees Celsius, right? So as soon as it gets the heat, the ice will start melting. So then we know that Q is ml from calorimetry, right? L of fusion. And from the first part, we know Q over T is 40, right? That means Q is 40 times T, and T is 12 hours, right? And because we want to measure how much mass will be melted, so Q is from calorimetry, or heat of transformation, latent heat of transformation. Q is m times L, right? And it's 40 times T is 12 hours. 12 you must convert into seconds, and then you solve for m. M is 40 times 12 times 3600 divided by L of F. L of F is the latent heats of transformation for fusion of ice, and that's from the table. So if you go back and check the formula, formula sheet or in the physical table, that's 33.3 10 to the power 4, and the mass of ice melt is about this. Okay, about 5 kilograms of ice will be melted during 12 hours period. So here's the next problem, and these problems are on radiation, rate of loss of heat, emission of radiation through, any object. It says the number 3 problem. A person with skin temperature 33 degrees Celsius is in a room, 24 degrees. What is the net rate? Remember, it's not just the rate of emission of radiation, it's net, right, of heat radiation by this person. So just to draw this picture, a person is standing, in a room. So there will be exchange of heat within, because this person is exchanging heat through radiation. He is radiating, mostly infrared, because heat radiation is mostly infrared, which you can't see. But at the same time, the room is also at some temperature, 24 degrees Celsius. It also emits radiation, which this person will absorb. The person is emitting heat at faster rate, more, because it has higher temperature. But at the same time, any object within that room is also emitting, radiation. But what will be the net? So the Q by T net will be what? So Q by T emission, right? This is by the person. We are calculating the net, exchange of heat, net rate of heat transferred by radiation for the person. So Q by T emission, right? Emitted by the person. You have to subtract the Q over T absorption by the room, right? Because room is also at some temperature. So this is the formula. So and Stefan's law says Q over T is E sigma area, right? And T4, T to the power 4. T is the temperature, person's temperature, minus E sigma A area of the person absorbed, because he's doing this absorption, right? And T, this is the room temperature, 4. That's it. So Q over T net will be E sigma A T4 minus. You can directly use this formula. That formula is given actually. So E is, it says the skin. This is the emissivity, depends on different surface. So let's use 0.97. Is telling you to use this. Sigma is Stefan's constant, which is always a universal constant, 5.67 10 to the power -8. This is called Stefan's number, Stefan's constant. Area is the surface area of the body. So it says for adults, use the surface area, total surface area about 1.8. And T to the power 4. So T is the, now here, since these are the individual temperatures, you must convert temperature into Kelvin, otherwise it won't work. Because since these are the individual temperatures, it's not just the difference, it's the power 4 difference. So 2073, right? So 306 Kelvin, and the room is at 24 degree. So 297. Okay, so you make sure you do this and then put it back here. So 3064 minus 297.4. Okay, so that's our answer. So about 98 watts. So you can clearly see human body, adult human body is effectively 90 watt, 98, about 100 watt heater, right? If you're staying inside a room, right, you're effectively radiating, you're effectively actually about 100 watt heater. So that's why if there are a lot of people in a room, you don't even need heating system in the house, because each person is 100 watt heater, and during the winter season you don't even need it if there are a lot of people in a room. So that's the reason. So next problem is kind of a conceptual problem, short question, So it says two thin square copper plates are radiating energy at the same rate. Remember, one is big, one is smaller. One has an area A1, let's say, right? And the other one has, it says, based on this question, other one has area A2. If this is length L, it says, the edge length, this is the edge length of the square is plate number 2, this is plate number 1, plate number 2 is 4 times that of plate 1. So its edge length is 4 times L. If this is L, the plate number 2 has its length is 4 times L. So, but they are radiating at same rate. The rate of emission of radiation is same based on the question, right? So then calculate the ratio of the temperature difference. So it's actually T1 over, so this is at temperature T1, this is at temperature T2. What is the ratio of the temperatures, right? So first, based on the question, since they are radiating at the same rate, right? So the power of emission will be said, power is just Q over T. Okay. So this is now E sigma A1, right? They have the same actually emissivity and same because they are both copper, right? So they must have same emissivity and sigma is always constant, but area is different. T14 on the other side, E sigma A2 T24. Okay, E sigma will cancel out because they are same for both, and we're solving T1 over T2. So T14 divided by T24 and T2 A2 over A1, right? But A2 is now, what will be A2? So its area will be, because its edge length is 4 times R, for 4 times 4, 16 times A1, right? Not just 4 times A1. So this area will be 16 times because its width is 4 times 4, right? So 16. So so 16 A1 divided by 16 because the second area is 16 times more than the first. So 16. One more step. This is T1 over T. So you can power 4. You can do the whole power 4 is 16, right? But it's actually, how would you find T1 over T2 ratio? So then you have to do 1/4, right? This is the 1/4 power. So that's your answer. So that is going to be 2. So temperature ratio is only 2. So its temperature must be double compared to this. Okay. Now next problem is on calorimetry. Remember, calorimetry has to do with the measurement of heat, and it has to deal with what factors of the given object is playing role in losing the heat or gaining the heat. It has to do with the heat gain or heat loss. Remember, go back and check the see my video on calorimetry. So it says 100-gram ice cube at negative, it says below freezing point, negative 10 degrees Celsius, is placed in an aluminum cup whose initial temperature is 80 degrees Celsius. The system comes into equilibrium temperature 30 degrees. 30 degrees Celsius is the equilibrium temperature finally. So you have aluminum cup, insulated aluminum cup, right? Is thermally insulated, and you put ice cube at negative temp. Initially negative 10 degrees Celsius, right? And after some times the system comes into equilibrium because the aluminum aluminum loses heat, ice gains the heat, right? And there's some so what would be the what's the based on this data, what is the mass of the cup, right? So here's the block diagram actually. So block diagram, first you need to understand heat loss and heat gain. So aluminum will lose heat, right? So here's the block diagram. So this is for aluminum cup, right? So aluminum has initially what temperature? Initially 80 degrees Celsius, right? Will go to what? Initially, because the final temperature is equilibrium temperature is 30 degree. But however, for ice cube will have a different step because ice cube is placed at below freezing point, so it can't directly go to 30 degrees Celsius. First the ice cube has to melt, right? The ice will first melt, right? To no, first ice cube will first go to 0 degrees Celsius first, right? First ice will go from below freezing point negative 10 degrees Celsius to 0 degrees Celsius, and then ice will melt. Okay, then ice will melt, then it will be, and this is a phase transformation, it's called heat subtransformation. So 0 degree ice to 0 degree water, right? And then it will go from 0 degree water to 30 degree water, right? Because we know final equilibrium temperature is 30 degree. So that's the step of heat. So for aluminum cup, right, it's easy. It's just one step. So it's cooling down from 80 degree to 30 degree. So just MC delta T, M aluminum, C aluminum, delta T, right? But here you have three steps. From ice to 0, since it's warming up, ice warming up, you use MC delta T, ice, right? From here to here, it's not warming up. It's getting heat, right? It's absorbing heat, but it's just changing the phase. It's a phase change. From here to here is phase change. So during phase change, we use what? ML, right? Fusion. And from here to here, again, water is warming out. So when something is changing its temperature, again, you use, MC delta T. So that's the three step. And we know that the total heat, we know from calorimetry principle, we know that calorimetry principle says Q of cup, the aluminum cup, plus Q of the ice has to be equal to 0. So that's what we will be using. So Q of cup is M cup, mass of cup, which we are solving, and it's made from aluminum, so specific heat capacity of aluminum, and change in temperature, which is 80 minus 30. 30 minus 80 actually, because you always use final minus initial. Plus, the Q of ice has three steps, as I said. So one is M of ice, C of ice, because this has not melted, so you have to use the specific heat capacity of ice, and delta T. Plus then phase change, mass of still ice, L of fusion, plus then from here to water warm up, mass of ice or water, C of water, delta T. So see, ice will exchange heat in three different ways that you have to understand. Okay, and that all equal to 0. So mass of cup, we don't know. We are calculating that. Specific heat capacity of aluminum, which again you can find from the reference table, is 2090. And change in temperature is delta T is always final temperature minus initial temperature. So final temperature is 30 degree, right? 30 degree. Minus initial temperature is 80 degree. Okay, and then what else? No, I'm sorry. This is 900. Aluminum has specific heat capacity of aluminum 900. Plus mass of ice, which is given. So mass of ice, 100 gram of ice, so 0.1, because we want to calculate everything in the standard unit. C of ice, which is the specific heat capacity of ice, is 2090, again from the table. What's the change in temperature from here to here? So 0 minus 10, 0 minus 10, 10 degree basically. Plus, now this, mass of ice, which is still 0.1, and this is the specific latent heat for fusion of ice, which is from the data again, for right 13.3 times the power 4. Plus last one is MC delta T for water. So water gone from here to here. So mass of water, mass of ice same. Specific heat capacity of water is which is 4190 if you see the table, and its final 30 minus 0. This all equal to 0. Now you have all these variables, so now just calculate all these, right? And solve for mass of the cup, because that's the only variable left. Now do this algebra and calculate this 1.06 kilogram. Okay, about 1 kilogram of ice will, this is the, the mass of the cup, aluminum cup, must be about 1 kilogram. So that's how you solve. So make sure you understand all these steps to solve this problem. So here's another problem on calorimetry. So it says, how much heat energy is required to melt and raise the temperature of 10 gram of ice at negative 10 degrees Celsius again to 30 degrees Celsius, okay? So it's just asking, you don't have to do heat loss is equal to heat gain, because it's just asking how much heat will be required to melt and raise the temperature of 10 gram of ice to, rising temperature from -10 to 30. So here's the steps. You must understand these steps. So first, ice is kept at below degree. It's at sub below, right? Sub freezing point is just like a deep freezer. So ice -10 degrees Celsius. So what will happen as soon as it absorbs heat? The first ice won't melt right away. First, ice has to go from -10 degrees Celsius to 0 degrees Celsius before it starts melting. Now it will melt to liquid phase. Now this is now no longer ice, it's water. And now finally water will go from 0 degrees Celsius to water will warm up and its final temperature is. So it's actually how much total heat, right, will be required during this process to do this. So then from here to here you use what, MC ice, right, delta T. From here to here you use ML again. From here to here you use again MC of water, right, delta D. That's it. So total heat required is, not just sum them up. Sum them all this is. Mass of ice, which is same, mass is same for all. But see specific heat capacity of ice, not the water, because it's still in ice phase. Plus ML, right? Plus MC of water, because now it has water phase. And that's it. So mass is 10 grams, so 0.01. C of I 2090. Temperature change is 0 minus 10, basically plus 10 degree, right? Final minus initial. Plus mass of a 0.01. This is the specific latent heat. This is 33.3 10 to the power 4 if you check the physical table. Plus the final one is 0.01. Mass is same. This is specific heat capacity of water. This is 4190. And temperature difference is final minus initial, so 30 minus 0. Okay, so that's the total heat required to do this job. So, and if you do this calculation, all this calculation is 4796 joules. So double check my calculation. So that much heat will be required to do all this, you know. So here's the next problem, little slightly different problem. You know, it says 100 gram of ice at 0 degrees Celsius into 100 gram of water at 20 degrees Celsius in an iron vessel of mass 100 gram. The whole system is thermally isolated. What fraction of ice melt? So here's the important. So whenever you see what fraction of ice melt, here only fraction of ice, percentage of ice will be melted here. Whenever you see problem like that, you have, right away you have to understand that since only fraction of ice will melt here, some ice will still be left. The temperature of ice plus water at equilibrium will be always 0 degrees Celsius. Temperature won't, if you put a thermometer, you know, and measure the temperature, you know, of ice and water at equilibrium, it will be always 0 degrees Celsius. It won't increase its temperature until all ice, you know, melts. So that's the most important part. So whenever you see a fraction of ice melt, you have to assume that the final temperature is always 0 degrees Celsius. Okay, that's the first important. Then first we have to check the ratio. How much heat will be given off by hot object and how much heat will be absorbed, you know, by the ice, you know. So then take the ratio. So first, heat given off by the hot object. Here hot object is Q of you know, Q of water, right? Because water is hot compared to ice, because water is at 20 degrees Celsius. And iron vessel, cup, right? These two objects are hot, so they will give off heat. So first you have to check this number. So the Q of water is mass of water, C of water, delta T, plus same thing, Q of iron vessel, C of iron, delta T. So, and we know final temperature is 0 degrees Celsius, remember, right? So mass of water is 100 grams of water, 0.1, and this is specific heat capacity of water, 490, and temperature is, so it will cool down from you know, 20 degree, because they are both at 20 degree initially, and cool down to 0 because we know that the final temperature is 0 degree. So that's the first assumption. So 20 minus 0. Iron vessel has 100 gram mass, same, right? iron, the specific heat capacity of iron, if you see the table 449, and again 20 minus 0. So if you do that, the Q, the heat given off by the hot objects is 9300 joules if you do that. Now let's check how much heat will be required to melt, completely melt the whole volume of ice. Ice is 100 gram, right? Ice is already at 0 degrees Celsius. So Q of ice melt, right? This is already at 0 degrees Celsius. So as soon as it gets heat, it will melt. So ml, right, from heat subtransformation. Mass of ice is 100 gram, everything is 100. So 33.3 10 to the power 4. So in order to melt a whole volume of ice, 100 gram of ice, you need that much heat. And if you do this calculation, so it's 33300, and you can clearly see this is greater, right? Q of ice melts, right? If you want to melt this, that you need that much heat is greater than Q heat given off. So heat gain is not equal to heat lost in this case. So that's the reason here you can't do heat lost is not equal to heat gain by ice. Why? Because check this number, they are not equal, right? So that's the reason only fraction of ice will melt. So how much ice will melt will be the fraction, just this fraction. So just take the ratio, and that fraction will be melted. Will be, so how much heat you have, right? Heat given off divided by heat required to melt, which we already know this now, 9300 divided by 33300. Only that much fraction of ice will melt. So it's about 0.28, which is 28%. Only 28% of ice, right, in this process will melt, and it's a only fraction, right, about 1/3. Why? And reason is, I told you, because heat given off by hot objects in this system is not enough to melt whole volume of ice. So now these are some, the last chapter these are some problems on thermal expansion of solids, right? So here's the first question, really easy problem. An aluminum rod has a length of 4 meter, exactly 4 in 4 sig fig, 4 meter at 20 degrees Celsius. What is its length at 350 degrees Celsius, right? Obviously its length will be longer, but how much? Yeah, right, at if you heat up to 350 degrees Celsius. And alpha, which is the thermal expansion coefficient, is for aluminum is that much. And that's a really easy problem. So you have delta L from, right, is L naught alpha delta T. That's from the thermal expansion of solid. It's from linear expansion. It's called linear expansion. That's the empirical formula we have, right? Check my lecture slide. That's it. So this is final minus initial length, and you're solving the final length, right? So final length will be, so if you add both sides L naught, you can simplify one more time. L naught is common factor, right? And 1 plus alpha delta T. Or you can, if you remember, you can directly use this formula. And that's it. So L naught is the initial length, which is 4 meter, exactly 4 meter, right? And 1 plus alpha is 23 10 to the power negative 6, and change in temperature. This alpha is with delta T. So delta T is change in temperature. Again, whenever you do delta T, you don't need to convert actually into Kelvin, right? So change in temperature will be final minus initial. So 350 minus 20. So that's going to be your final length. So 4.03. So just a little bit increase, and that is expected because the solid expands very little. Okay, so that's going to be the final length, right? So only little percentage increase. So here's the next question on thermal expansion. So it says a copper flask vessel is full of olive oil, right? It's just filled with oil, right? That means the initial volume is same, the initial volume, right, is 150 centimeter cube. At initial temperature, what initial temperature? 60 degrees Celsius. Now you heat it up, right? You raise the temperature. Now obviously, right, some oil will spill, right? Some oil will spill, and you collect it in a separate vessel, say. So it says how much this volume, right? Let's say delta V, this V, right? How much oil will be spilled if you raise the temperature, right, of the whole system from 60 degree to 31 degrees Celsius. That's it. And beta is the cubical expansion, volume expansion coefficient. It's given for oil. That's for copper is this. Okay, that's the question. And the reason actually the oil will spill, because here this copper, right, and you have oil. Oil expands more, right? Obviously, because it's liquid. Oil expands more than copper for the same increase in temperature. So this is easy. Actually, the main concept is actually this: the volume of oil spilled, right, has to be the expansion in the oil, volume in oil, right? Because we know that oil expands more. This is delta V, not just V. Delta V of this is the expansion of oil, actually the expansion of volume expansion of oil minus the expansion of the copper, right? That's it. The difference has to be the extra volume of oil spill. That's the main idea. So delta V from our volume expansion, right? This is initial volume, right? Initial volume is same for both. Beta of oil and delta T minus volume is same for both. Initial volume is same. Beta of the copper and delta T. Delta T is also same, and that's it. So initial volume is 100. So just let's keep it, calculate everything in centimeter cube, and your final answer will also be in centimeter cube. So beta of oil. Oil has 0.68 10 to the power -3. Change in temperature is, again, you can just keep it in Celsius 6 minus initial volume is same. The beta for copper is 5.1 10 to the power -5, very, and 31 minus 6. So that's it. So volume of the oil spilled will be that the difference, the differential expansion, difference between the differential expansion, right, will be this, and that's it. So 2.4, but what's the unit? Centimeter cube, not meter cube, centimeter cube, because we kept this as centimeter cube. So that much volume of oil will be spilled during this process. So here's the last problem, and here's the question. You have a steel rod, initial diameter exactly 3 centimeter at some room temperature 25 degrees. A brass ring has an interior diameter of 2 nanometers, slightly less at 20. This is initial temperature 25 degrees Celsius, right? So brass ring then doesn't fit because its interior diameter is slightly less than the steel diameter. Now you can make it fit, so you just heat it up, right? And you know from the data, actually this brass expands faster than the steel. If you see, check the expansion coefficient, because alpha for brass is bigger than alpha for steel. So if you heat it up together, since brass ring will expand more than copper, I mean steel. So then at some higher temperature, we have to find that out. At what higher temperature it will just fit. Okay, so that means the final diameter of the steel ring, a brass ring, and equal to the final diameter of the steel rod, right, based on the question, and then just fit. If that happens, it just fit, right? So diameter, first of all, you have to understand diameter expansion is linear expansion, because you are measuring the diameter, means you are measuring the length, right? Diameter, the whole thing will expand. So you are measuring the length, linear expansion. So you have to understand diameter expansion is linear expansion. And linear expansion formula, right? D final is one of the formula 1 plus alpha delta T. This formula is gives you the relationship between final and initial diameters, right? You can directly use. Now, from here, we know D final brass ring, right, must be equal to D final diameter of the steel rod. And the final diameter is given by initial diameter of the ring, 1 plus alpha for ring means brass, delta T. Change in temperature will be same. And the same thing here, initial diameter of the rod, 1 plus alpha for steel, because rod is steel. And then just put all the numbers and find the final. First you solve for delta T, right, for if you want to simplify it. First solve for delta T, and then doesn't matter. So D of initial diameter is 3 centimeter, right? No, wrong, 2 point. So just let's keep everything in centimeter. That's the ring diameter. 1 plus alpha for brass is 19 10 to the power negative 6, and then delta T is with alpha, remember, is final temperature, which is what we are solving. My initial temperature is both at 25 degrees Celsius. Okay, right hand side, same, do this. Rod has a diameter of 3 centimeter, exactly 3 centimeter, right? Big bracket. 1 plus alpha for steel is 11 10 to the power negative 6, and change in temperature is with alpha, actually, is final temperature minus 25. Change in temperature for both same, right? And now you do distribution, so I will leave it up to you, right? You have to distribute and solve this algebra, right? Solve this algebra, and then you will find that out. So double check, make sure you do the complete calculation. About 360 degrees Celsius. So this brass ring will exactly fit with the steel rod at about 360 degrees Celsius. You have to really heat it up, right, from 25 degrees Celsius to 360 degrees Celsius if you want to fit the brass rod. So that's how, this is the main idea. The main idea is their final diameters are equal. Okay, so that's how you solve it.